To start, we open our general relativity maxima file, change the metric tensor from that of special relativity to our uniform acceleration case. So for the first spatial coordinate, we have minus e to the 2a x1. For the time coordinate g44, we have e to the 2a x1 without the minus sign. Run the code that does all of the differential geometry calculations. There's our metric tensor, just to check it, make sure. Now we look at the curvature tensor. All the components are 0. That means the space-time is flat. And that means there must be a transformation that will convert us to an inertial frame, freely falling global inertial frame. And we said in the main video that that transformation was psi is e to the x cosh t minus 1, tau is e to the x sinh t. So we put those in for psi and tau, and now we're going to look at the metric. The differential of tau squared minus the differential of psi squared has a bunch of trig functions, so we do trig simplification, and there we get our result we originally started with e to the 2x dt squared minus dx squared. So we verified that indeed that is our transformation. Now let's take a look at velocity. So let's, for the spacecraft at x equals 0, we have psi is cosh t minus 1, and tau is sinh t. So the velocity is the change in psi, the differential of psi over the differential of tau, and we see that is indeed sinh t over cosh t, as we said, which is the so-called hyperbolic tangent of t. We could plot that. And there we get our characteristic hyperbolic tangent curve from 0 to 1.